So far, we've looked at simple temperature simulations where each cell or object evolved on its own, independent of the others. Of course, that isn't very realistic. Now that we're comfortable with fancy iterators, parallel algorithms, and execution spaces, let's tackle a slightly more complex scenario, the 2D heat equation. This illustration shows the computational stencil that we'll use. Each cell's temperature in the next time step depends not only on its current temperature, but also on its four neighbors, left, right, top, and bottom. In code, the 2D heat equation might look something like this. Don't worry about the specific math or constants here. Instead, try focusing on the data access pattern. First, we read temperature from the left and right neighbors of a given cell. A 2D array is typically laid out in row major order, meaning each row is placed sequentially in memory. To find a flattened 1D index of a 2D row column index, we can multiply the row index by the width of our grid and then add the column index. Row times width jumps us to the start of the correct row because each row has width elements. Adding column then offsets us within that row, taking us to the specific column. Using the same pattern, if we went to the left neighbor of a given cell, we just subtract 1 from the column index. For the right neighbor, we add 1 instead. Similarly, we compute the indices of top and bottom neighbors by subtracting and adding 1 to the current row index. Besides that, we incorporate the previous temperature of a given cell. This code works fine in most of the cases, but there's one issue. Real grids aren't infinite, so cells along the edges don't have all four neighbors. If we tried to compute the left neighbor for the leftmost cell, for example, we'd go out of bounds. To prevent that, we need to handle boundary conditions. In this course, we're using constant boundary conditions. This means that we won't update the temperature for boundary cells. They keep their original values. The next question is how we actually launch this computation on our 2D data. If you think about it, each cell in our grid corresponds to a single ID in a flattened one-dimensional space. So we can just use the thrust make counting iterator to generate all possible cell IDs, and then transform those IDs into updated temperature values. But we still need to figure out which row and column these flat IDs correspond to. We use division and modulus to reverse the process we used to flatten the matrix. This way we can map each flat index back to its correct 2D position. After that, the rest of the code has the same boundary check logic that we used before. Essentially, we're just transforming cell IDs into next state temperatures without needing an explicit loop over rows and columns. Notice that we're capturing the pointer to our temperature data in a slightly unusual way. In standard C++, calling .data on an std vector returns a raw pointer, but with thrust containers, .data returns a typed iterator instead of a raw pointer. Thrust needs that type information for various reasons, which we'll explore later. For now, the main point is that you can convert this typed iterator to a regular C++ pointer by using thrust raw pointer cast. This gives us the in-pointer variable that we can capture in the lambda. We can start by initializing the entire grid to a low uniform temperature and then set some higher temperature values at the top and bottom boundaries. If we run our heat equation transformation with those initial conditions, we get results that look a bit like an empty oven heating from the top and bottom. Over time, you can see the heat spreading into the cooler regions, all according to the stencil computations we just set up. An important thing to remember is that thrust isn't limited to algorithms that match the exact signatures of the C++ standard library. If there's a common pattern that can be accelerated on the GPU, thrust often provides a specialized algorithm for it. A good example is thrust tabulate. Under the hood, it's really just transforming a counting iterator, something which we've seen is quite common, so thrust gives it a dedicated name and interface. The call looks just like thrust transform, except that there's no input range to pass in because the input is implicitly generated by tabulation. Besides being more convenient, specialized algorithms like this are often more optimized. So if you spot an algorithm whose name and purpose match what you need to do, it's a good idea to use it. Let's take that next step and replace thrust transform with thrust tabulate. Notice we don't need to create a counting iterator anymore. Tabulate generates the indices internally. The rest of the code stays exactly the same, so it's a straightforward swap. This makes our intent clearer and code easier to read. We'll likely need to convert from the flat 1D index to 2D coordinates in more than one place, so it's best to follow the dry, don't repeat yourself principle and put the logic in a separate function. That's what the row call function does here. It returns a standard pair of the row and column calculated from the flat ID and grid width. We've marked this function as host device so that it can be called by both the CPU and the GPU. Then in our lambda, we can use structured bindings to unpack the pair directly into row and column variables. This keeps our code clean, makes it easier to maintain, and avoids scattering the same formula in multiple places. Unfortunately, the C++ standard library doesn't know anything about CUDA, so functions like std_make_pair aren't marked as host device. Calling them inside device code triggers a compilation error, like the one shown here. Calling a host function from a host device function is not allowed. So what are our options here? Do we have to re-implement every standard library type just to make it device friendly? Fortunately, we don't have to do that. Recall from the stack diagram that thrust is built on top of libq++. Fortunately, we don't have to do that. Recall from the stack diagram that thrust is built on top of libq++, a core library that provides host device-friendly implementations of many standard C++ vocabulary types. For instance, it provides types as pair, tuple, optional, variant, complex, and atomic. Not only do these types carry the proper host device annotations, but they're also optimized for GPU usage. That means you can treat them as drop-in replacements for the usual C++ types, and they'll compile and run correctly on both CPU and GPU. Let's see how to swap out std_pair for the libq++ equivalent. The actual change couldn't be simpler. We just prefix CUDA to std_pair, making it CUDA std_pair. And now our code compiles and runs without issues. The same pattern applies to other standard library types. Just pull them in through CUDA std instead of std, and you'll have GPU-friendly optimized equivalents. CUDA std_pair isn't the only type that can clean up our code. Right now, we're still manually converting between 2D row column coordinates and the 1D indices. That approach works, but it's easy to make off-by-one mistakes and other indexing errors. It's also not very expressive. You have to remember the exact formula for flattening coordinates every time. It might not be too bad when we're just flattening 2 dimensions, but as soon as you go beyond that, things get ugly quickly. Take a look at this snippet. It flattens a 5-dimensional set of coordinates into a single index. It's easy to make a mistake in code like this. It even includes a comment to show what the actual intended indexing is. Wouldn't it be nice to use a standard C++ type that could make this type of indexing actually compile? CUDA std mdspan is a non-owning, multi-dimensional view built on top of a flat data array. Think of it like a lightweight wrapper around your memory. You give mdspan the dimensions, for example, height and width in the 2D case, and it automatically handles the offset calculations. Because it's just a view, there's no extra memory or hidden overhead. It's practically zero cost. Using mdspan results in cleaner code and fewer bugs. The illustration here shows how a 1D array of 6 elements can be treated as a 3x2 grid through mdspan. Because mdspan doesn't own memory, you need an underlying buffer that holds the actual data. In this example, we've created a CUDA std array of 6 integers, 0, 1, 2, 3, 4, and 5. mdspan will then view these values in whichever multidimensional shape we specify, but the data itself remains right here in our array. Let's construct an mdspan based on this array. For this case, we have to pass MDSpan three things. First, we need a raw pointer to the data. Here we use the array.dataMember function, which returns a raw pointer. Remember though, if you have to construct MDSpan on top of a thrust container, you'll need to use raw pointer cast. Besides the raw pointer, we'll have to provide the number of rows and columns. That's all MDSpan needs to treat our 1D array as a 2x3 matrix. Once the MDSpan is set up, you can access the underlying sequence using parentheses. Just supply the row and column indices, starting with 0. For example, passing MD parentheses 1, 2 returns the element of the second row, third column, so a value of 5 in our case. Besides the direct element access, MDSpan also provides some handy helper functions. For instance, calling MDSize returns the total number of elements in the view. In this example, that would be 6. Additionally, MDSpan lets you query the size of each dimension using the extent method. For a two-dimensional view, calling MDExtent0 gives you the height and MDExtent1 gives you the width. In this example, MDExtent0 will return 2 and MDExtent1 will return 3. This is essentially the order at which we provided these values in the constructor. For the exercise in this section, instead of capturing a raw pointer in our lambda, we'll capture an MDSpan. That way we can use multidimensional indexing directly without manually flattening the row and column into a single index. It'll make the code cleaner and less error-prone while maintaining the same performance.